Professors John Spidell. We're Team 13, in case you need that for your little sheets. And we're going to walk you through our overall analysis for the production of tripropylene glycol from propylene oxide. Okay, good to know. As an overview of our process, the justification is tripropylene glycol is used in many applications. The uses of tripropylene glycol range from industrial solvents and industrial lubricants to paints and coatings, all the way down to personal care products. Currently, the market is mostly using monopropylene glycol and dipropylene glycol, which I believe the last group talked briefly about. However, tripropylene glycol is a useful substitution for all of these products, and as the markets become more saturated for use of propylene glycol and dipropylene glycol, tripropylene glycol will become more important. Our original process goals were to manufacture 30 million pounds of propylene glycol per year. However, when we did our economic feasibility study of this, we found we weren't going to break even at 30 million pounds of tripropylene glycol. Instead, we used the economy of scale and scaled up to 60 million pounds of propylene glycol per year. At this number, we found we will not only break even within 7 years, but have a large rate of return on a 20-year plant life. Next, Ben is going to walk us through the reaction chemistry.
Right, so due to the low yield of the production of tripropylene glycol directly from propylene oxide, so therefore we have to go through like two intermediate reactions. So because we didn't use the catalyst, so on the reaction will happen at like high temperature. So the first reaction will be involve propylene oxide reacted with water. So we got the propylene glycol. So you can see on the slide the mechanism is easy to understand. Right here, the hydrogen will attach to the oxygen and breaking the bond between the oxygen and the base group. So leaving the base group with the positive charge, and after that the hydroxyl group of the water will attach to the base group and create the propylene glycol. And because at high pressure, so we want to keep on the reactant in the liquid. So having a high temperature, we want to keep on the reactant in the liquid form, therefore we can increase the pressure. And then the second intermediate reaction will involve propylene oxide, react the propylene glycol, and make the dipropylene glycol. So again, so the hydrogen of the propylene glycol attached to the oxygen and breaking the bond between oxygen and base group. So therefore, and after that, the oxygen of the propylene glycol then attached to the base group again and formed by the dipropylene glycol. And the final reaction will involve from propylene oxide and dipropylene glycol and make the main product dipropylene glycol. And right here, the mechanism is the same as the second reaction. So for further understanding about our process, so how we talk about it.
Alright, I'm going to talk about the process of the plant. So in front of you is a typical plant to make monopropylene glycol, and we use this as a reference for our tripropylene glycol plant. So the plant contains a total of 3 reactors, plug reactor 1, 2, and 3, and 4 distillation columns, and also 3 recycle streams. And the target is to make 60 million pounds of tripropylene glycol in the end, and we want to minimize the tetrapropylene glycol. But I'm going to walk you through each stage of the process. So first, we have propylene oxide react with water in the first reactor. Based on the reaction chemistry, the main product is coming out. The first reactor is monopropylene glycol, but we also have other glycol products, including dipropylene glycol, and tetrapropylene glycol. We also have water left unreacted from the first reactor, and then we feed that stream into the first distillation column. On the top of the column, we want to separate water, and that water stream go back to the reactor number 1. On the bottom of the product, on the bottom of the distillation column, we have glycol products, including monopropylene glycol, all the way to tetrapropylene tetrapropylene glycol. We then feed that into the second distillation column, as shown in here. So on the top of the column, we want to separate monopropylene glycol and further react with propylene oxide in the flow flow reactor number 2. In order to minimize tetrapropylene glycol, we want to control the ratio between propylene oxide and monopropylene glycol. And we found that we can convert 40% of monopropylene glycol to dipropylene glycol, left 60% of monopropylene glycol left unreacted. And then we feed that into the first distillation column, is then further separate into downstream. Next, we have the bottom of the distillation column number 2, we have dipropylene glycol, tripropylene glycol, and tetrapropylene glycol. Is then fed into the third distillation column. From here to the top, we want to separate dipropylene glycol and then further react with propylene oxide into reaction number 3. Reactor number 3. Again, we want to minimize tetrapropylene glycol. We want to control the ratio between propylene oxide and dipropylene glycol. We find that 30% of the reactants converted to tripropylene glycol, 70% to dipropylene glycol, and then feed that into distillation column number 2, when we find that the optimal point. Lastly, we have the bottom product is then fed into the final column number 4. And on the top we have our desired product, which is tripropylene glycol, and on the bottom we have our byproduct, which is tetrapropylene glycol. And by using Aspen simulation, we can find that the purity of the product is about 99%. And now Cass will talk about the optimization of the process.
Okay. After finalizing our actual process, we began looking at different ways to optimize our yield of tripropylene glycol. The first thing we considered was adjusting the ratio of water propylene oxide in our first reactor. A major concern was how this would affect the temperature that we should run the reactor at. So we ran a parametric analysis to compare the composition of monopropylene glycol in the first reactor to the mass ratio of water propylene oxide in the first reactor, and we varied this over a range of temperatures. The bottom line is the temperature is a composition of 150 degrees Celsius, second to 160 degrees Celsius. And the third line is a range from 170 to 240 degrees Celsius. So as you can see, with a very small deviation in the composition for a wide range of temperatures, we're able to confirm that the ideal temperature doesn't change much with the ratio of water propylene oxide. So we're able to focus on the ratio first. In this graph, we have the composition of the various components of the first reactor. For the purple line is monopropylene glycol, and the bottom blue line is our heavy tetrapropylene glycol. In that particular reactor, we were trying to maximize the production of monopropylene glycol. From literature values, we initially assumed a low water propylene oxide ratio of 0.4. However, by running the sensitivity analysis in Aspen, we were able to figure out the maximum production is somewhere around 2.3 to 2.4. We decided that we would sacrifice a small amount of monopropylene glycol to continue to reduce the heavy production and optimize the process due to the high cost of separating the heavier tetramer. After coming up with the ratio, we then moved to optimize the temperature for each of the reactors. From the literature values, we started off with a temperature of around 240 degrees Celsius for the first reactor. Using sensitivity analysis, we were able to bring the temperature down and achieve the same exact composition to around 197 degrees C, greatly reducing energy costs and utility costs for the entire project. Our final optimization is on the number of stages in each of our distillation columns. This is the second distillation column we're looking at here. Started off with around 20 stages to ensure that we would achieve a full separation of components. However, we see here where the stages aren't actually contributing to the separation process. So by optimizing, we reduced the number of stages down to 8, and we adjusted the feed inlet location of the distillation columns to match the composition at that individual stage. Again, in this graph, we see the composition of each individual component and the number of stages at the bottom. We weren't able to reduce all the columns to 8 stages, so we'll be able to reduce them all significantly. Doing so reduces the size of the distillation columns and cuts back on the cost. I'm going to move on to Matt to talk about marketing.
So all chemicals in our plant are safely biodegradable. No products of biodegradation exist in any of our raw materials or products produced throughout the process. Additionally, all toxicity tests resulted in negative results with the exception of propylene glycol, which has a LD50 value rated of 5,000. Because this number is very high and propylene glycol is rarely found in its purest form anywhere in the plant, no precautions were needed to be taken for this. 0.03 gallons of water are used per pound of tripropylene glycol produced, so we have this indicates a very low level of wasted water in our plant. No greenhouse gases are produced anywhere in our process, and our product stream is less than 0.01% of any of the raw materials entering our plant. All the chemicals we use can be extinguished with water in the event of a fire, making it easy to keep them under control. The only problematic property that we have is propylene oxide's flash point of negative 37.2 degrees Celsius. Because this number is so low and will obviously room temperature is above this, the raw material storage tank for propylene oxide is temperature and pressure controlled and is constantly and precisely monitored to ensure nothing goes wrong with that. Everywhere in the plant operates below water emission temperature for any of our chemical raw materials or products. And while the reaction is exothermic, cooling jackets are located in any necessary spots to keep the temperature under control. In the event of a runaway reaction, CO2 foam sprayers are located above the reactors to immediately shut down the reaction if a runaway reaction were to occur. Looking at our plot plan, all 3 reactors are compiled on top of each other, meaning that if our CO2 foam sprayers are activated due to a runaway reaction, all reactors will be shut down immediately and the process will stop completely. Additionally, our PO storage tank is located near the loading dock area, so in the event of a chemical spill or a fire, any chemical cleanup teams or fire companies can easily access the area and take care of any problems necessary. PO storage is also located very far from the control room where any people will be located, so it keeps them at a safe distance from this. Water storage is kept in between our propylene oxide, which is our only dangerous component, and our final product storage tanks, which is TPG. So the chances of a problem with the PO storage tank reaching our final product storage tank is very low. Ruth will now talk to you about our economic analysis.
Thank you. All right, so as we were doing our process analysis, we were also running an economic analysis. As I mentioned in the overview, we originally had a goal of 30 million pounds per year, and we were not economically feasible. Luckily, we were doing economic analyses at the same time, so we scaled up to 60 million pounds per year. In order to understand all of the economic analyses we ran, we're going to walk you through 3 different analyses that we ran. First is the base case economics, where we assumed a 20-year plant life. Based on that 20-year plant life, we found that we had a break-even during production year 7. After the end of the 20-year plant life and breaking even, we have a net present value of $9 million. After knowing and comfortable that we would break even, we ran a sensitivity analysis to understand what parameters most affected our break-even and our final economic profitability. Based on this sensitivity analysis, we found that we were most sensitive to our revenue, or any increase in product price and raw material costs. Our other costs, such as operating labor, utilities, and capital investment, were not as significant. Finally, because we're so sensitive to our product sales price and our raw material costs, we ran some analysis through the available literature and the market research and tried to figure out, well, what might happen in the future to our product cost. Based on the literature, we found that our product price is expected to increase while our raw material costs will be fixed to inflation. Because of this, we expect our overall profitability to be more than the base case analysis and for it to increase proportionally to any increase in our profitability or our product cost. So to start with, we're going to go over our base case. The graph, which is the most interesting part of this slide, is our cash flow on the y-axis in millions of dollars. On the x-axis is the year of the plant life. We start by assuming -3 because we assume a 3-year build time. This is very conservative, but we wanted to run a worst case scenario analysis. During year 0, we are most in debt because that's when we are fully built but not yet operational. We assume a $4.58 million investment. But during the course of the plant life, you can see we're positive all after our break-even year in 7. This is because our process is non-corrosive and non-hazardous, so we're expecting to not have to replace major equipment or shut down for major repairs. At the end of year 20, we expect to have a net present value of $9.34 million. This is a return on our $4.58 million investment of over 204%. Because we are profitable, we wanted to then run our sensitivity analysis on why we're profitable and what we might be sensitive to. This graph shows on the x-axis variance in several different parameters, and on the y-axis the effect it has on our net present value in millions of USD. The orange line is the line of revenue. It is positively correlated between increase in revenue and increase in net present value, which makes sense. However, the little brown line is actually all of our other parameters, which were found to be insignificant relative to the rise in revenue, or variance in revenue. For good housekeeping, we did zoom in to show you that our fixed capital investment, utilities, and labors all have about the same effect on our net present value. However, their effect is about 40 times less significant than any variance in our revenue costs. Knowing that our revenue cost was a particular area of perhaps trouble, we tried to run forecasts on how our revenue might increase or decrease according to the market. Currently, Dow Chemical makes most of the tripropylene glycol. However, the market seems to be small and it's not well documented. Instead, we found a lot of literature on monopropylene glycol and dipropylene glycol, which the market seems to be nearly saturated because it has so much demand. We expect the sales price for tripropylene glycol to rise as these markets become saturated, because tripropylene glycol is an acceptable substitute for many of these products. Conservatively, we might see 10% growth in tripropylene glycol costs. However, our raw material cost is expected to only grow with inflation, or about 3% per year. A 10% increase in the growth of our sales price translates to 6 times more growth in our net present value, or an overall net present value of $60 million, which is a 1,200% return on investment. We're now going to walk you through conclusions based on all of the wonderful things we just covered. Our process is efficient. We've reached our target of 60 million pounds per year. We produce 62 million pounds per year. We have low water waste, low environmental impact, and for a safe process, both for our operators and for the environment. We're also feasible. We have a reasonable rate of return even on our worst case scenario, and we have the potential for future capital reduction and possibly the potential for increased revenue. Thanks, I'm going to walk us through our recommendations.
Right, so after doing the design, so I would like to come out with some recommendation. So for the first design, our design is economically very feasible. And if we want to move from the design to the real production, we have to do more detailed job work on our design, like project control to control the other equipment for temperature, pressure, like reactor and distillation column. And but for further future improvements, so we can reduce the number of columns of distillation column for example, like you see on the plane, on the plane narrator for distillation column, we can reduce column number 2 and 3 into one column. And right now, like potentially we can like collapse our whole process into like only one column or one reaction process. So this is a reference, and so thank you for listening, and if you have any questions, please.
Any questions?
What's the difference in product value between propylene glycol and tripropylene glycol?
We're selling we expect to sell tripropylene glycol for $3.35 per kilogram, and we buy propylene oxide at about $2.20 per kilogram. However, we do expect, if we would like to receive the propylene oxide, which is our initial raw material, from a refinery by direct pipeline, so we might be able to get it for cheaper.
Do you know what the price for just monopropylene glycol is?
I think it's above $2. It's slightly more than the tripropylene glycol price currently. I think it might be closer to $3.50. We did consider selling it as waste stream instead of having recycles, but as part of the scope of our project, we figured it would be better to focus on tripropylene glycol.
Okay, any more questions? Very good. That way, somebody had a hand
Is
up. Mine too.
considered a tax rate in your revenue off the place where the plant's being located?
We're planning on building our plant in Texas because we want to be near oil refineries so we can take advantage of the lower cost of propylene oxide. And Texas also has a favorable tax rate for manufacturing of 35%, which we did factor into